Hello, everyone. Thanks for coming. So today we're hosting Valeri Vardanyan, who is a postdoc at KAVLI Institute for the Physics and Mathematics of the Universe in Tokyo. He's going to talk about amplification of gravitational waves in the early universe. And floor is yours, Valeri.
Yeah, thank you. Thank you for inviting me. Today we are going to talk about gravitational waves, mostly produced in the early universe. And since it's only a few of us, please, feel free to interrupt, and maybe we can make this like less formal. Right. So since I was not very sure about the audience, I thought I might start very from some wide introduction to what we do in cosmology, because I'm a cosmologist, mostly interested in phenomenological aspects. But I realized that some of the people in the audience might not know much about cosmology, so I thought maybe it would be a good idea to give some broad overview. So the current picture of the universe that we have is that we think in the early universe, there was an epoch of so-called inflation, which solves a couple of issues of the non-inflationary scenario. I will talk a bit about this just to be sure all of us are on the same page. Perhaps more importantly, inflation not only solves those issues, but also generates the seed of structure in the late universe, the large-scale structure of matter, and also the cosmic microwave background anisotropies. How this is done is not how inflation works precisely is not known, and it is a topic of active research. But there are some simple models which work pretty well already. So one of the simplest working scenarios is that there was some dynamical scalar field in the early universe with some flat potential, and this flat potential produces the curvature fluctuations, which, as I mentioned, serve as a seed for the late universe. And so I will talk about those a bit more concretely, but just because I have it here, let me mention. So the prediction is that so the spectrum of the curvature fluctuations is predicted to be almost scale invariant, and observationally we have already verified that this is true. So we have seen not only that the spectrum is almost scale invariant, but we have even measured the slight violation of scale invariance, which is predicted from this simple inflationary scenario. So this is about the curvature perturbations, which kind of source the overall structure, large-scale structure of the universe. Besides that, inflation also predicts presence of gravitational wave background. So this gravitational wave background is originating from vacuum fluctuations, and because there are tensor degrees of freedom, there are also quantum fluctuations for those tensor degrees of freedom, and similarly there is a prediction for those. So I will talk about this a bit more, because this is kind of the main theme of today's talk. But for now, let me just mention that those are not detected yet, but those are actually considered to be like holy grail for cosmology at the moment. Like if those primordial gravitational waves are detected, it would be kind of like be considered as a smoking gun for the inflationary scenario. But also it's very cool and exciting because those gravitational waves are thought to be like kind of quantized quantized metric perturbations. So in a sense, if you detect those, you would indirectly detect some aspect of quantized gravity. That's pretty exciting. Unfortunately, directly you cannot measure them, but interestingly enough, they leave some particular polarization imprint on the cosmic microwave background. And there are some planned surveys. So you might have heard about LIGHTBIRD mission, which is going to measure this polarization precisely and yeah, hopefully it can detect something. For the late universe, I will not stop on this much, but our model is the so-called lambda CDM, which assumed general relativity and cosmological constant. However, so even though this is established, but there is just from observation side, since I'm a phenomenologist, I always think about the data. So from data point of view, there is still a big discovery room out there. So it's not very tightly, lambda CDM is not still very tightly constrained. So there is still a big room for alternatives. For example, there could be some extra degrees of freedom, some scalar fields minimally or non-minimally coupled to gravity, or some other scenarios, and so those are also very actively being studied in cosmology. So far I mentioned that the primary observables so far have been like cosmic microwave background was very important for establishing the cosmological model, but also like there are some galaxy surveys which measure the large scale distribution of matter, which is the second most important kind of like probe of the universe. And now we are in the era of gravitational waves, and since today's talk is about gravitational waves, like I cannot resist to mention that we have already detected gravitational waves, and this is here is kind of like a cartoon summary of the current catalog of all the gravitational waves that LIGO Virgo detector network has measured. So it's order 100 events. So those come from mergers of astrophysical sources. So those have nothing to do with early universe, but still it's cool to know that we can already detect gravitational waves directly. So in a sense, we know that they exist. So I will not stop on this much, but essentially, yeah, so these astrophysical gravitational waves, sometimes you might hear that, oh, this is like a new window to the cosmology. I think that's true because those sources, the gravitational waves provide alternative probe to cosmological models. You might have heard about so-called Hubble tension. Like I mentioned, the lambda CDM model, which is the standard model of late universe cosmology, is compatible with, is the valid model, but there is some tension in it concerning specific value of the expansion rate of the universe at the present time. And gravitational waves actually offer a way to measure various cosmological parameters in an alternative way. So basically, independently of standard probes, CMB and LSS. Yeah, so those were about particular gravitational wave sources, like mergers of compact objects. But on top of that, there is also expected background of gravitational waves. So gravitational waves, which are not like some of like if the source of gravitational wave is too strong, then it would be resolved, and LIGO Virgo will detect them. But if there could be also some weaker gravitational wave contribution, which does not constitute as a separate resolved event, but there could be some background of these gravitational waves. And many probes, like more prominently this LISA satellite, is gonna try to measure any of those backgrounds if they exist. So those backgrounds can originate from astrophysical sources again, but they can also be linked to some fundamental physics, some phase transitions, or some other stuff which I will more concretely talk later today. And so interestingly, this background is also like is not measured yet so far, but there are, so the current data is becoming sensitive enough so that we can already place like upper bounds. And so we kind of already have an idea about rough idea of how much, what's the overall amplitude of background at various frequencies. Just kind of like a small summary slide of what you can do with various types of gravitational waves, and mostly what I have worked on. So obviously there is like exponentially large room, which I haven't mentioned here. So those are just some topics which I have had the chance to work on. So with astrophysical gravitational waves, you can actually try to measure various aspects of gravity. Like here, I'm showing the propagation law of tensor perturbations on cosmological backgrounds. And in general relativity, all those terms in boxes are, so all those extra functions are zero. But in principle, there are interesting alternatives which allow for some time and space variation of those coefficients. And with astrophysical gravitational wave observations, you can actually try and measure those. So that's quite interesting. Today, mostly I will focus on this second aspect, which is about gravitational waves produced in the early universe. So nothing to do with astrophysical gravitational waves. So it's a bit kind of like a schematic here, but what we will explore today is whether we can have amplified gravitational waves during inflation. So I will explain more concretely what I mean by that. And actually, this point is quite it's connected to something called primordial black holes. So those are black holes which are produced in the early universe, and this idea of induced gravitational waves, which again here is just schematic, but I will tell what they are exactly. So those induced gravitational waves are related to the idea of primordial black holes, and again, this is an active field in cosmology. Many groups work on that. I'll skip that. This is just about this thing that I was mentioning with gravitational waves observations. You can test various aspects of gravity, but in this talk, I will assume that gravity is GR, so no modifications. And we will be talking about early universe, about the inflationary stage. So probably all of you know those things, but just as a let me quickly set the definitions so that we are on the same page. So at the large scales, the universe is described by such a metric where the single degree of freedom is this scalar function called scale factor, which describes the relative expansion of constant time hypersurfaces. And the expansion rate of this function is known as the Hubble function, so it is h here. And the time change, relative change of this Hubble function with respect to time is what we typically call a slow parameter. At late universe, this is not small, but for inflation, as I will mention shortly, this should be actually slow. This should be actually small. So that's why it's called slow parameter, mostly motivated by inflationary terminology. So this metric is conformally related to Minkowski metric, and without assuming the existence of inflationary states, just in standard cosmological scenario where you have radiation domination, matter domination, and cosmological constant domination at the present time, kind of the beginning of the universe or the initial kind of singularity, this when the scale factor goes to zero, the conformal time, this conformal time variable, also goes to zero. So because of this, there is this well-known issue that like if you look on the sky, like at cosmic microwave background, points at different different directions look pretty much the same on relatively large scales. But if you look at their causal paths, they were actually not in contact in the past, so they couldn't have had chance to be in contact with each other. So that's this horizon problem in standard cosmology, which in case of inflation is resolved. Like if you have the accelerated phase in the early universe, then you can extend these points to arbitrarily smaller values, and then the points could have been in causal, they could have causally interacted with each other. So that was the primary motivation for inflation, why it started at the first place. But at the moment, that's the current understanding is not that inflation is needed for solving the horizon problem or like flatness problem. So it's mostly attractive because it predicts the perturbations that we observe in the universe, or the statistical properties of the perturbations that we observe. And let me quickly show how that goes. So at the background level, like if we look at large enough scales, the universe is homogeneous and isotropic. And as I mentioned, the simplest model of inflation assumes a single scalar degree of freedom with this equation of motion. And then there is the Friedmann equation with this equation of motion. If this epsilon parameter is smaller than 1, then universe accelerates, the expansion of the universe accelerates. Inflation requires so if the inflationary potential is flat enough, then essentially this epsilon, this Laurel parameter, is much smaller than 1, which means that the energy density is dominated by the potential. And in order for this phase to last for long enough, you need this second Laurel parameter to also be small, which essentially requires that the second derivative is smaller than this friction term and the forcing term in the equation of motion. So just as a summary, inflation requires that, so inflation is a phase with a constant Hubble function, or almost constant Hubble function, so it's a de Sitter phase, and scalar field dynamics is just very simple. So this was about the background dynamics. Obviously, we care a lot about perturbations, and when we consider perturbations on top of this homogeneous background, for the metric, we can write like around FRW background. The most general form of perturbations that you can write, linear perturbations, I should mention, are of this form. So you have some cross terms, and you have those scalar functions, and you have this function here, which encodes gravitational wave degrees of freedom, so propagating degrees of freedom. And yeah, so it's not very important, but yeah, so those for example, this function contains some scalar degree of freedom as well as purely vector degree of freedom. So kind of different helicity modes decouple at linear order. So gravitational waves, vector modes, and scalar perturbations evolve independently from one another, at least in general relativity. And I should emphasize that this is about linear ordering perturbations. Right, so having this form of the metric, and as well, so we need also to specify the perturbations of the energy momentum tensor. So here is some generically perturbed perfect fluid equations of motion. Sorry, the components of the stress energy tensor. So there is obviously we are working in the framework of general relativity, and there is an issue of like all those variables that I was describing. Not all of them are physical. So some of them are gauge redundancies, which can be are not physical degrees of freedom. In order to be able to compute something physically observable, we can find some gauge invariant combinations. So there is this zeta function and this calligraphic R function, which essentially measure the spatial curvature on various constant, on various hypersurfaces. So this zeta one is constant energy density, measures the spatial curvature of space. So a spatial curvature of constant density hypersurfaces. while this calligraphic R measures the spatial curvature on hypersurfaces with constant value for inflaton, so constant inflaton slices. They are in principle different, but for inflation, during inflation, you can show actually that they are essentially the same thing. So we don't need to worry much about the distinction. So we will mostly work with this calligraphic R, which is again good quantity to calculate because it's gauge invariant, but also it is related to curvature perturbations. Just one more comment about terminology and kind of about what concepts we want to calculate. So obviously, all those fields are stochastic fields, so we cannot predict the particular. So we cannot predict the value of the field itself, but we can predict the statistical properties, like we can predict the two-point correlation function, for example, which is measured by the power spectrum. Sometimes in the literature, you will see this dimensionless version. And for cosmology, an important thing is that we want to also measure the scale dependence of this power spectrum, so this NS. NS equals 1 means you have a scale invariant power spectrum, but as I was mentioning, the current observations already have established that this NS is close to 1, but slightly smaller than 1. Similarly, for primordial tensor fluctuations, you can do the same. You can define similar quantities and similar tilt for the tensor power spectrum. So the goal is kind of to predict. The goal in cosmology has been to predict those power spectra. Just in order to show a specific calculation, like what is, so this is like well-established, those are well-established results within simple inflationary model, this single scalar field model. So here I'm specifying a concrete gauge in which those scalar field fluctuations are absorbed in metric curvature. So all the degrees of freedom are actually in metric curvature fluctuations. And these Hij are propagating tensor degrees of freedom. So because we know the theory of gravity, we can derive equation of motion for the dynamics of those guys. So we can derive, like, if we are interested in linear order equations of motion, and we can write down the second order action for those. So we can canonically normalize this action. So we can introduce some variable, which, so this step is very simple, but historically it has been important. So this variable has a name, it's Mukhanov-Sasaki variable. And then, yeah, you can have the second order action for this. Then having that action, you can proceed and quantize those fluctuations. So you can have the equation of motion. So you can promote those functions into operators. And you can have basically you can write down the equation of motion for the mode function, which looks like this. In curved space, so basically in cosmology, we are doing kind of like poor man's version of QFT on curved backgrounds. So in QFT on curved backgrounds, there is an ambiguity in choosing the vacuum. One way this is fixed in cosmology, so again, it is there is no unique vacuum, but so the results will change if you choose different vacuum state. But one thing which is conventionally done and like kind of yeah, so it's kind of based on physical considerations. You try to fix the mode functions, the vacuum and the mode functions, and so the way this is done is that, so we decompose our fields into modes, and there is a certain limit, like if you go infinitely past in time, for a given mode, you will essentially, there will be a regime in which this particular mode does not feel the gravity. So it kind of lives in Minkowski space. And you can specify the vacuum for the Minkowski space, which is unique. And then this specifies the mode function at later times as well. So this is called Bunch-Davis vacuum. This is what is conventionally considered in cosmological in cosmology. And yeah, now you have the solution of the mode function. So here, this is kind of like simplified version. So this assumes pure de Sitter, but as I mentioned, it's like this Lorel parameter is not exactly zero. It's just small, but not exactly zero. But actually, this pure de Sitter kind of gives reasonable results, and you can also calculate the Lorel corrections to those results, but the results do not change much. So yeah, in the Sitter limit, you can then take those mode functions, this decomposition, and calculate the power spectrum of curvature perturbations, which turns out to be this thing. So one important thing I forgot to mention is that this variable, this calligraphic R, so it evolves when it's smaller than the so-called Hubble horizon, but then as soon as it crosses the horizon, it becomes frozen. So it does not evolve. So what we need is to calculate the power spectrum at the time of horizon crossing for the particular mode. And it turns out that yeah, so this is the expression. So all those variables should be evaluated at horizon crossing. And because actually inflation is not exactly de Sitter, but is quasi de Sitter, like the different modes exit, so there is slight time variation of this thing. And then because of that, the spectrum develops certain tilt in the, so it's not exactly scale invariant. So all this is to say that what I was saying in the beginning, that inflation predicts quasi-scale invariant spectrum for curvature perturbations can be shown, yeah, with such calculations. And for scalar field, the spectrum scales as h squared, so the Hubble squared. Similarly for tensor fluctuations, so you can do the same thing for tensor modes. So you can quantize the tensor fluctuations, and you can derive the power spectrum for tensor modes. So this is the primordial power spectrum of tensor modes. For scalar fluctuations, observationally, we have already detected them. So like Planck mission has like very precisely measured the scalar fluctuation. So this power spectrum is precisely measured. Like I was showing a figure in the beginning that even the shape of this spectrum is measured very accurately. But tensor ones are not. So essentially the scalar one is fixed. So one important kind of quantity that you can introduce is the so-called tensor to scalar ratio, which is the ratio of the two spectra. So this denominator is fixed. And as I was showing here, the tensor spectrum probes the Hubble function, which is the energy scale at which inflation happens. So essentially, if you measure this R, which is the goal of those missions that I was mentioning earlier. So if you measure this tensor to scalar ratio, you essentially measure the energy scale at which inflation happened. So the current limit for R, so R is not measured yet, but there is an upper bound on it. So the kind of observationally, we know it's the exact number I don't remember, but it's of order of 0.1. So we know it's smaller than 0.1, but we don't know the exact value yet. So that's why, yeah, so it's kind of this 10 to minus 2 is an interesting benchmark point that upcoming surveys, if this R is really 10 to minus 2, upcoming surveys should be able to measure it. And if that's true, then that would fix the energy scale of inflation to be around 10 to 16 GeV. one other thing which the tensor to scalar ratio fixes is how much the inflaton field can travel during the evolution, during inflationary evolution. So can measure the field excursion. And depending on the value of R, so if R turns out to be larger than this, so there is model dependent prefactoring from, but this overall structure is robust, so it does not depend on specific details of particular inflationary scenario. And yeah, so if this R is large, then it would mean that your field has traveled super-Planckian distances in field space. So based on this, inflationary models are typically classified as small field and large field models. And so this would basically, detection of R would mean that, you deal with a large field model. So the field has transversed distance is longer than the Planck mass, which could be problematic. Like if you tend to think about inflation, like we don't know the microscopic model, but maybe based on some EFT arguments, we can construct some effective model. Typically, you would need this delta phi to be sub-Planckian. So in that sense, preferred models are the ones with delta phi smaller than m Planck. But at the same time, if the standard kind of law is true, those small field models predict very small value of tensor to scalar ratio. So essentially, those small field models are not testable with gravitational wave observations. So that's one shortcoming.
So just a quick question. So can we say that this experiment is basically to rule out the large field models?
Yeah, so if this are like this is kind of the target, like if it's measured to be around at this level, then essentially small field ones are ruled out. But and the opposite, if R turns out to be much smaller, then you rule out the large field models. Yeah.
I see. Yeah. So I mean, but from the perspective of like preferred models, it's probably you wouldn't test anything, and then you rule out the large field models. Then you have to come up with new experiments for testing the small field, right?
Yeah, but if it is like a small field, like if this delta phi is like, I don't know, too small, then essentially, what you're saying is that ideal, like in principle, we can always design some experiments which would measure smaller and smaller values of R. But in practice, I think that there are some details which I will skip, but just because of technical difficulties, you cannot go arbitrarily low. So it's kind of the current understanding is that if it is low field inflation, then it's essentially untestable, maybe in the foreseeable future with gravitational wave detections. Gravitational wave.
And the reason why people believe that it has to be delta phi has to be smaller than m Planck is related to locality or what?
Locality argument I haven't heard. So it's mostly.
I just guessed. I haven't heard either. I'm just asking. Yeah, I'm not familiar.
No, I haven't heard such an argument. So the argument that I know is based on EFT. That if you so if your field travels for a long distance, you would probably expect some large corrections to, for example, to your potential. And also, so I'm really not an expert on that, but from string theory side, there is a conjecture that actually, there is what's the name, sub-Planckian distance conjecture, that actually the field, it's conjecture that in string theory this delta phi cannot travel for longer than Planck, than m Planck.
anything we don't know, there is a string theory conjecture about. So
Yeah, exactly. But again, so I cannot I cannot say for sure, but what I understood from talking to experts, so there are various conjectures, as you mentioned. There is like even a conjecture saying that inflation is not allowed in string theory. But this one, this sub-Planckian distance conjecture, I think is the one which most of the people kind of trust. It's kind of like there is a small consensus that that kind of should be true in string theory. But anyways, yeah. So from phenomenology side, this is what you have. Like if you don't have anything on top of your inflation, then small field models are essentially not testable with this CMB gravitational wave observations. But this was actually gravitational waves from vacuum. So far we talked about gravitational waves from vacuum. So an interesting question, which recently actually gained a lot of momentum in the community, is that in principle, at linear order, as I was saying, scalar and tensor fluctuations are decoupled from one another. So scalar fluctuations cannot source the gravitational waves. But if you go to second order, even in general relativity, scalar fluctuations, like here I'm showing the relevant action. So you have your gravitational waves and you have scalar degrees of freedom, which, if you remember, were the metric degrees of freedom in this original perturbed metric that I was showing. So at second order, they can source the gravitational wave degrees of freedom. So there are some induced gravitational waves in principle, which even if the vacuum result, if vacuum contribution to gravitational wave is small, you can have this amplified induced gravitational waves. For standard inflation, so roughly like you can have some naive estimate that the amplitude of like this is kind of like the fractional energy density in the universe for those induced gravitational waves, which are induced, which are sourced by second order curvature fluctuations during inflation. So because this power spectrum of curvature fluctuations is already measured to be small, and now this is even second order, so it's tiny, so you expect a tiny contribution. However, so this is on very specific length scales. So this argument, this measurement of scalar fluctuations is on very specific length scales. So here in this diagram, I'm schematically trying to show what I mean. So, so this line is so-called comoving Hubble radius. So it does not matter much what it means, but during inflation, this basically goes down. In standard cosmology, this goes up. And what I told you in words earlier is that if you have some perturbation with certain at certain scale, then it evolves when it is below this horizon, it is inside the horizon. And then when it crosses the horizon, it's frozen. And then it re-enters the horizon now, or like in a late universe. And then when it re-enters, it sources, yeah, so there should be also CMB. So it sources large scale structure and CMB fluctuations. But that's only limited scales. So CMB and large scale structure do not measure, so they only measure a tiny portion of accessible scales. So here, this figure, it's small, but on this axis, it's Fourier modes. So those are the scales. And there are no constraints on smaller scales. Like on much smaller scales, this power spectrum does not need to be scale invariant. So it can have some features. It can potentially be very large, actually. So there are absolutely no constraints. And since there are no constraints, there is this interesting idea that if you would have large enough power spectrum, So power spectrum essentially measures the variance of fluctuations, of curvature fluctuations. So if this variance is large enough, then on the tail of this distribution, you might have huge overdensity, which then could collapse into black holes in the early universe. So you might have heard about primordial black holes, which are exactly that. So earlier on during inflation, those modes, which are relatively large modes, exit the horizon and source the observable kind of standard observable large-scale structure and CMB. But at much smaller scales, the scales which exit the horizon during inflation much later than the observable scales. So if you kind of postulate that there is some large enhancement of the power spectrum, then those could decay. Those, when they enter the horizon, the entire horizon could collapse into a black hole. So there are. So this is also being very actively studied from different angles. One is that how you can have this enhancement in the power spectrum, then how exactly this collapse to black hole is happening. So this is kind of really like interdisciplinary field. Like people from numerical relativity are contributing and people from cosmology are contributing. So it's kind of like a lot of work is being done here. Okay, so those primordial black holes could be sourced, could be formed, but also because you need this large enhanced power spectrum in order to form primordial black holes, they are necessarily coming with induced gravitational waves, so non-linearly induced gravitational waves. So this effect, which was small on those scales, it can actually be large, very large on much smaller scales. Okay. Yeah, I will skip this. So it's just so those primordial black holes are interesting not only from the context of these induced gravitational waves, but they can also explain the LIGO-Virgo events. So they can be the LIGO-Virgo events. So there are some estimates ranging from 97. Already there have been some ideas in this direction. And okay, so here comes the primary topic of today's talk, which is that on the small scales, you can form primordial black holes. So you can have enhanced curvature fluctuations, and those enhanced curvature fluctuations can source additional gravitational waves. So the question is, can you have induced gravitational waves at the CMB scales? So because if you could, then essentially this Lyth bound that we were talking about earlier will not hold anymore. So you will have the vacuum contribution, but if you have some large contribution from non-linearly sourced gravitational waves, then this will not hold anymore. So it's basically, the question is there a counter example to this Lyth bound? It turns out so people tried before, like there are some groups from the US, like a couple of groups, so several groups tried this, and the general understanding was that it shouldn't be possible, and the schematic understanding of why this shouldn't be possible is the following. So you have your gravitational wave equations of motion, and you want them to be sourced by some second order scalar fluctuations. So yeah, schematically those should source gravitational waves, and the induced power spectrum for those tensor modes, as I was schematically showing earlier, should scale as the square of the power spectrum of this delta phi. So power spectrum itself is quadratic in delta phi, and then this is fourth power in delta phi. So if delta phi is small, this is tiny, but if delta phi is large, this could be large. So that's fine. But then at the same time, this delta phi is also sourcing the curvature. Like if this delta phi is the inflaton, is the field which drives the inflation, then it also produces the curvature perturbations, which are very tightly measured. So there is an effect to curvature power spectrum. So this is, I should have written induced here and here. So both of these are those are the nonlinear contributions. So the linear contribution we calculated earlier, and that's okay, we don't touch that. Those are the nonlinear contributions from this kind of source. So there is this 1 over epsilon square, which is, if you might remember that in the relation of this R with delta phi, there was 1 over background phi dot, so 1 over slow roll. So this is basically suppressed, like, or I should say enhanced by slow roll parameter. However, if you look at the tensor to scalar ratio for those, it scales as slow roll parameter squared. So since slow roll parameter is small, the scaling of this is not very promising. So essentially it tells you that you cannot induce this a lot. However, what we thought is that you can have some additional field in this picture. So this field could, so again, this delta phi is sourcing gravitational waves. So this is as before. Now you can have some, but now we assume that this delta phi is not the inflaton field. So this does not directly couple to curvature perturbations. So those delta phis do not directly source the observed curvature. But instead there is some intermediate, so this is the inflaton field. So there is another field which derives the inflationary dynamics. So if you want, this phi field is like secondary spectator field during inflation, not producing the curvature perturbations. So if you forbid any coupling between this phi and chi, so there still will be gravitational coupling, because of which this delta chi will receive nonlinear contributions from delta phi. However, if you propagate this nonlinear effect to curvature power spectrum, you'll see that actually the induced R scales as epsilon to power 0. So this is good. So it's not suppressed by epsilon. It's not suppressed by small slow roll parameter. So now, so this was the idea. Now we wanted to show that this actually works, like concretely show that this works. Yeah, so again, just to repeat, so this delta chi is essentially the inflaton, the chi field is the inflaton, phi field is some massive field, and we want these delta phi fluctuations to be amplified somehow. We will rely on a mechanism which is used a lot in a field called yeah, like when inflation ends, universe should reheat somehow. So all the inflationary energy should translate into standard model particles. And for that, there is a stage called preheating and reheating after the inflation. Basically, when inflaton goes down to its potential, it starts to oscillate. And then there is an effect of parametric resonance, which parametrically translates the energy of inflation of inflaton to standard model. So we want to rely on a similar idea. So this delta phi will be amplified by, will be resonantly amplified. Although I should mention that the exact amplification mechanism is not the crucial thing here, is that you could amplify this delta phi maybe with some other mechanism, but this resonant one was maybe the most natural one. And then, yeah, so this delta phi is the amplified one. And then just, yeah, so here, how this parametric resonance works in practice, like if you have a differential equation like this, and if these coefficients P and Q, even if they are order 1, if they satisfy, like if they are in those bands, then actually the solution of this equation exhibits exponential amplification. So there is exponential enhancement. So that's the whole idea of parametric resonance, that with order 1 coefficients, you can have exponentially large fields. So our theory is very simple. So we have those two sectors. So this potential, there is no interaction with those fields, so two decoupled sectors. This V of chi, well, we specify some more favor, like some well-studied model of inflation, but it does not matter what inflationary model you exactly study, you exactly choose. It's some valid inflationary potential here. For phi sector, we need to have some oscillations, which is, okay, so at this point, we just write down what we need, but in principle, these kind of oscillatory terms appear in various string theory constructions. So we take that as motivation, but at this point, that's not even very important. But yeah, so this phi is an oscillating field. So before I show you the mode functions, so the background dynamics of this phi and chi is as follows. So there are those oscillations. And then, okay, oscillations end. So there is this intermediate, so those figures you should treat from left to right. So the time passes from here and it goes like this. The important thing here that essentially this phi field will, so it has oscillations and at some point it will be stuck in one of the minima of those, of its potential. And it will not be dynamical anymore. And because it is not dynamical, in order for a given field to contribute to curvature perturbations during inflation, it needs to be dynamical. Because one way to think about curvature perturbations of inflation is that at various patches of the universe, because at one patch the field value is slightly large, the other one is slightly low. So time is basically time till the end of inflation in different patches is slightly different. And then if you evaluate the curvature at this final patch, you will see the perturbations. So what I'm trying to explain here is that if a particular field becomes non-dynamical, like if the background is not evolving, then it does not contribute to the inflationary dynamics anymore. And those time fluctuations are controlled by the field, which is still dynamical, which is in our case is this chi. So you can show this more mathematically, that this curvature power spectrum or the curvature modes. So there is this thing which is essentially a time variable. So it's called e-folding, but it's like is the logarithm of the scale factor. So if this if this e-folding does not depend on one of the fields, then that field does not contribute to the final curvature power spectrum, to the final observed curvature. And because this phi field now in our case becomes non-dynamical, all the scalar curvature is determined by the chi field, by this field, which remains dynamical all the way until the end. Okay, so we have the mode functions for those two fields. This field has this oscillatory piece because of that oscillatory piece. So you can map this equation into an equation called Mathieu equation, in case you are familiar with that. So it's not exactly Mathieu because there is some time dependence in the coefficients, but it turns out to be okay. Then the bottom line is that those delta phi modes are exponentially amplified. And then we have an expression for the amplification factor. So there are various parameters of the potential. So those things appeared in the potential which I specified earlier. The essential thing is that this amplification factor can be huge, can be exponentially large. Here is what happens. So delta chi modes evolve. So this red one is what you typically have in standard inflation. These delta phi modes are now parametrically amplified. And then because it is stuck at one of the minima, when you solve the mode functions for a massive field on de Sitter background, you can show that it decays when it is outside the horizon. So we correctly recover the expected behavior. But here is one issue. So these delta chi modes, we want them to source the curvature power spectra. But when we write down the equation of motion, we see actually that delta phi source is delta chi. So even though we explicitly assumed no coupling between delta phi and delta chi, still this delta phi source is delta chi. And the reason for this is that you are always coupled gravitationally. So this is because of gravitational coupling. In the paper, there is an argument. I will not, probably I don't have a lot of time left, so I will not stop on this, but essentially you can do some rescaling of the parameters. So we show that there is a large parameter space based on some rescaling that we can do, which allows for this term to be tiny. So by appropriate choice of this P and Q coefficients, we can essentially have get rid of this term while keeping this amplification factor large. So we can have large amplification without affecting these delta chi modes. And numerically, in the explicit numerical solution, you see that this is true. So this red one is not actually affected by delta phi. So it's as if this delta phi would not be there. So there is this second term here, which I will talk about in a minute. But for now, let's go to gravitational wave part, because we are primarily doing this for producing gravitational waves. So there is this source term in Fourier space. These second order terms are convolutions. So you have this convolution integral on the right-hand side. So we solve those numerically and calculate the power spectrum of the resulting tensor modes. And the result is, so you can forget about like, so there is some parameter control. So you can choose the parameters and have amplification at various scales. So these red and black ones are essentially the same thing for two different parameter choices. Let's focus on the red one for now. So let's focus on the red one. And so this is the resulting induced tensor power spectrum. If this mechanism would not be there, so we have some inflation given like fixed energy scale, it would predict this gray dashed line. So it would predict very small tensor power spectrum. While with this amplification mechanism, instead we amplify it enormously on a particular scale. So compared to this vacuum, or I should say, compared to the, both are vacuum, but like compared to the standard gravitational waves, this is amplified by many orders of magnitude. So there is some discussion about, so similar nonlinear sourcing would also exist for the scalar modes. So we should make sure that the scalar modes are not, so those are typically suppressed, but we need to make sure that those are not spoiling the observable predictions for the curvature spectra. So I will probably make sense to not stop on that much, but I should mention that we did that check carefully. So we took into account the effect of this nonlinear term. So I haven't written down the explicit form of the nonlinear term, but it's essentially similar to this. So it's again a convolution integral. And then we do this. We make sure that this does not back react to this chi sector significantly. Maybe let me discuss this, and then I will tell about the implications. So as I mentioned, so this spectrum is not, so we, on certain scales, we can measure gravitational waves directly, but those corresponds to extremely low frequency gravitational waves, and there is no experiment planned for that. So the way to measure those extremely low frequency gravitational waves produced during inflation are through cosmic microwave background, like imprint of those gravitational waves on cosmic microwave background. And this is something, so this is yet another spectrum which we calculated. It does not matter what exactly it is, but it's like, it's certain polarization so you have the CMB on the sky, and you can calculate the statistical properties of the resulting CMB map on the sky. And this is the power spectrum of fluctuations of so-called B-mode polarizations, which can only be produced from gravitational waves. So there are also some other effects which I will skip for brevity, but essentially, if you measure those B-mode spectra, then you are measuring some primordial gravitational waves at very low frequencies, which is exactly what inflation predicts. So this gray one is what this standard inflation would predict without our amplification mechanism. In order for this signal to be detectable, you need to be above this orange line, above this green line. So this is kind of projected sensitivity for upcoming experiments. And because we, by construction, choose a low scale inflation with small field excursions, so it's like small field inflation, the predicted signal is tiny, is extremely small. But with our amplification mechanism, we see that we actually can go above the detection sensitivity, and actually we can produce a detectable signal even in low scale inflation. So that's the bottom line. So yeah, let me see. So by the way, yeah, so the same mechanism can be used. I was mentioning that for forming primordial black holes, you need some mechanism to enhance this curvature power spectrum. So my collaborators studied this in context of primordial black hole formation, which is, in a sense, is easier task because you don't need to deal with this spark reaction issue to the curvature power spectrum on observed scales here, because there are no constraints here. But yeah, so this is an interesting mechanism for PBH formation by itself. There has been some, so this is not the only scenario in which you can beat this Lyth bound, and so these constraints that I was mentioning earlier, this Lyth bound and the energies, this fact that in low energy scale inflation, gravitational waves are, the amplitude of gravitational waves is very low. So in our scenario, that's not true anymore, but there is, clearly this has been of interest in the community, and many groups have worked on that. So there is one scenario in which this seems to be working. It is based on some gauge construction. So I will not go into details here, but yeah, essentially, if you have a model like this, apparently you can. So apparently, this SU2 gauge sector can source gravitational waves as well. So this is another possible mechanism for achieving the same goal, but not with scalar fields, but with a gauge sector and with much more ingredients, if you want. Yeah, this is their predictions, which I will skip, and yeah, just for the implications, I will. Okay, so gravitational waves are important for the early universe, because with that you can kind of have a smoking gun signal for the inflationary scenario. However, and also, yeah, so you can amplify the gravitational waves in the universe. So what was considered to be difficult seems to be actually possible with our explicit construction. The main implication for that is that, first of all, the low energy scale models of inflation are no longer untestable. So they are rendered, that they are now testable in this in the context of our construction. And it's also not only that, but it's also important because now a detection of B modes, So it does not mean that you probe the kind of quantized gravity. It could mean that so you could have gravitational waves produced during inflation, not only from quantized graviton modes, quantized tensor modes, but also from induced gravitational waves. So that's kind of shifts the view of how we would interpret the B mode detection. So this parametric amplification actually, so it has some interesting features. So there is some idea that we came up with and we are working with, not related to gravity. I mean, it is related to gravitational waves, but it's mostly about amplifiers. So in cosmology, there is a problem of like there are observed magnetic fields in the universe, and it has been another challenge to try to produce them during inflation, and it has been difficult because if you produce them during inflation, typically it back reacts on inflationary background too strongly, so that it spoils inflation. We seem to have an interesting idea which avoids this based on parametric resonance behavior. In this case, we are dealing with something called Hill-Whittaker equation. So it's an equation of this form, and it has similar instability charts as what I was showing earlier, but this is a bit more complicated, and we are trying to figure this out. Yeah, if by any chance any of you have is an expert of this type of equations, let me know. I might have a question or two to ask, but yeah, essentially that's it. Thank you.
Thank you very, very much, Valeri, for a very interesting and clear talk. Really, we learned a lot. So do we have any questions in the audience?
Hey, yeah, sure. Can I ask something?
Sure.
So if you have if your tensor modes are about the same scale as the size of at the horizon size at recombination, then do you have to worry about, I mean, obviously your tensor modes are having a big effect on the primordial plasma, but do you have to worry about the back reaction of the primordial plasma, like silk damping or something on your tensor modes and ruining this nice resonance you've got?
Yeah, probably, yeah, there could be some back reaction problems, but this is much smaller scales. So it's not exactly like a horizon size modes, right? So it's in that sense, it's similar to the standard gravitational waves, like in standard scenarios. It's just the amplitude.
Because I saw your curve versus K, and you had things like 10 to the -2 inverse megaparsecs, and that's co-moving, I guess, right? So wouldn't that mean something like 100 kiloparsecs at recombination?
Yeah,
I just divide by Z.
Silk damping is so it's smaller scales, right? If I recall it correctly. Like,
well, I mean, you had a pretty big curve. Yeah, so this is the curve I was talking about, and you have a pretty big range over where it could be. So silk damping, I would have thought would be, you know, hundreds, 10 to the 5 parsecs or something back then. So maybe 10 to the 8 now, but that's something like the very edge of your curves, no?
Okay, yeah, I thought silk damping is on smaller scales, but I could be wrong.
Well, no, maybe. Well, I don't know. It's all by within a couple orders of magnitude, anyway.
Yeah.
Yeah, I mean, usually it happens around K equals 1,000. I mean, L equals 1,000 or something.
Yeah, it's extremely small, like small angular scales. Yeah. I mean, yeah, we obviously haven't discussed any of that, so it could be, but would it be really coupled to the like there is no anisotropic stress really there, right? Like is it?
Well, the plasma should somehow respond, no? If you have, I mean, this thing is coupling gravitationally. It's, I mean, it couples to the gravity pretty well.
That's true. That's true. I mean, one thing is clearly that the observable that we are measuring is those B mods, which is because those gravitational waves are coupled to plasma. So I take it back. It is coupled to plasma. I'm not sure.
Because sometimes when you have a resonance, I mean, it's really sensitive to even small couplings. So. No, sorry,
Right.
go ahead. I didn't mean to interrupt.
No, yeah, we haven't actually thought about that. So one thing maybe I could say is that the resonance itself actually is happening much earlier, like it's during inflation.
Yeah.
And if there would be some couplings of some extra fields, so there is no plasma or anything at this stage. So one thing maybe what you're along the lines of your question is that if you would have some additional fields during inflation which would interact with this phi, then the structure of this equation could be modified, and you could have no resonance at first place. So like I would say maybe interactions during inflation maybe are more worrisome than interactions with interactions of already produced plasma, of already produced gravitational waves with CMB plasma. So I see your point that, yeah, so if there are some interactions, this resonance structure might be sensitive to that.
I mean, clearly the interactions go one way, so the question is how much they go the other way.
Yeah. No, for the inflation for the CMB part, we haven't really discussed that actually.
Okay, thanks.
Yeah, thanks for the question. That's interesting.
Sure.
Thank you. Do we have any more questions?
Maybe I could ask one, but it's just a very, very general one. So my general feeling is that it is very model dependent on every statement that one makes. So is there any general statement one can say, for example, that we expect certain gravitational waves from primordial that is completely model independent? We know that this should be.
Yeah. So so I agree. So this is extremely model dependent, but that's kind of like was the point of this. So because it's very difficult to do this, our point was to come up with one example, with one completely working example.
Mm-hmm.
Yeah, so we thought about it, like how would you try to, for example, this no-go that I was describing, like this is a general argument, right? So it's kind of like a general no-go argument. So in a sense, what we do is we want to find a counterexample to this no-go. That was our primary goal. So of course, it would be nice to have a general counterexample, which unfortunately is very difficult actually. Yeah, so it's not easy. Yeah, so it relies on a specific model to
I mean, I would say that usually it's good that most of the time it doesn't work, and sometimes it works. That means that there is something special with the model, or like it's not a generic feature, but yeah.
No, that's definitely, yeah. You can think about it from two different sides. Yeah, like one is that it's not. Yeah, I see what you mean. But no, actually, yeah. So it turns out to be quite difficult.
Yeah.
You need to specify various things.
Yeah, it's just you need to come up with an argument why is this specific case where it works, why is it more natural in some sense, right? Or I don't know.
Yeah, there are some technical discussions which I will definitely not go in detail, but so we kind of have thought a bit in that direction. Like, where is it? So I was kind of sketching here some conditions, and some of those, like for example, this third one. So it's a very technical requirement, but we kind of roughly have some guidelines of what kind of behavior you would need from your system in order this to work, but it's not very generalizable. Yeah, so we kind of have an idea of why it's difficult, but it's not very clearly formulated. So there are some conditions like about this mass should be small at the when it's done, when it has done its job, it should become small later on. Stuff like that. Yeah. Any other comments, questions?
Yeah, maybe just a comment. The thing which always bothered me more than the model dependence is the dependence on the initial condition. I mean, this Bunch-Davies vacuum. So how far away can you get from the Bunch-Davies vacuum and still have the whole paradigm work? I mean, is there any idea?
So that's in a sense a comment about inflation in general, right? Because
yeah. I mean,
no, that's a very good question. Yeah, so people don't work on that too much, unfortunately. Like in the community, it's kind of like everyone is using this vacuum choice. But I know some work is like there is. I don't know much about it, but there is this alpha vacuum thing, which is kind of like the Sitter invariant vacuum. There is some work I have seen on that. So basically, yeah, the dependence of the inflationary predictions on the vacuum choice is not very actively explored, unfortunately, but yeah, so some people work on it. So the results definitely will depend on it. Yeah, they will change if you choose a different vacuum.
Okay, thanks.
Thank you.
Thank you. I have a very general and perhaps naive question. So is it possible to kind of pinpoint some specifically quantum effect, like in everything that is happening? Like, I mean, is there like a boundary that you can draw between like classical and quantum in these considerations?
So those things are entirely quantum, right? So those are from vacuum fluctuations. But later on, so I'm definitely far from an expert in that, but the way I see how this works is that so you have some state, like some mode, which is like its vacuum as it is at its vacuum. But then because there is this time dependence, essentially like the potential for, like, imagine you have a harmonic oscillator in a potential, and then suddenly you change the potential, and the states effectively becomes classical in the end. So even though we started quantum, like all those calculations are quantum, but in the end, the observations are actually purely classical and stochastic, just stochastic classical fluctuations. Like CMB, there is no quantumness on CMB. When it comes to observations, it's just classical stochastic field. Because so it's yeah, so it's there is this classicalization kind of transition which happens because of time dependence of mode frequencies, or yeah, like effective kind of frequencies for in mode equations. Does it make what I'm trying to say?
Well, kind of. I mean, so would you say that the you know, the state globally, if speaking of a global state, you know, has any meaning? I mean, does it remain pure?
Pure. Okay, that's a good question. Yeah, that's yeah. But
if you want, I would say that a pure state always remains pure. I mean, you start with the pure state and you act on it with a Hamiltonian. So this, when you say that it's becoming classical, I mean, it doesn't really mean that you're doing any kind of crazy traces over the state or anything. It just means that effectively different parts of the superposition become different superselection sectors up to an extremely good approximation. And so there's no interference between them. And so when you measure, since you don't see any interference, you say, well, okay, nature has chosen one of these classical states. But that's really just an approximation which comes out of the unitary dynamics. You're never actually going to a density matrix as long as you started out in a pure state. So
Yeah,
everything you can do here with the unitary.
Unitary, yeah, everything is unitary, definitely. Yeah. One thing is that I don't know how much this relates to this classicalization thing. So at some point, like this example, which intuitively I think about it through that example, which is that, so you have your harmonic oscillator for a given potential. It's just the vacuum wave function. And then you reduce the mass, like, I don't know, exponentially, but your state is still there. So you have a state, but now a different, like a potential with exponentially lower mass. So this state kind of looks like high occupation number state now in this new potential. It's like suddenly your vacuum state is now a high occupation number state. It's part of what happens. But yeah, I haven't worked on this thing at all. So I don't know much how I don't know the current status of how this is understood, like how those quantum fields become classical. It's probably related also to what Jora was mentioning.
That's interesting. So in this view, you would say that the perceived temperature of CMB is basically a result of you measuring it locally. So basically, it just indicates that so basically you detect correlations between the field components, right? I mean, because otherwise you wouldn't see a temperature if it's in a pure state.
Yeah.
Very interesting. Thanks. So do we have any more comments or questions in the audience? Well, it seems the audience is out of questions, so so I shall thank everyone, and thank you, Valeri, again for the very interesting talk and
thank you.
interesting discussion. Bye bye, everyone.